Welcome to our last topic for scientific measurements. And this is also a very important topic because dimensional analysis is really a fancy word for using a lot of conversion factors at once. A lot of people, they see this word dimensional analysis and it kind of freaks them out. I think it is kind of a scary sounding word. But again, y'all, all it means is just using multiple conversion factors. In the lesson on conversion factors, we looked at that generic formula of how to think about jumping from unit to unit. So I'm going to expand that out a little bit. So we start with 1 unit, starting unit, and we're going to multiply it by a chain of other conversion factors, and along the way we're going to cancel out the units we don't want until we finally end up at the unit that we do want. So conversion number 1, and then we're going to multiply by conversion number 2, conversion number 2, and I'm running out of room. But y'all, so on and so forth, until you end up at your desired unit. So it's just a game of basically crossing out numerators and denominators. Example number 1. How many seconds are in a 40-hour work week? So what we start out with is 40 hours. And again, remember, we can think of this as being over an invisible number 1, right? Fractions have cool properties. So I'm going to stepwise go through the process of basically crossing out units until I end up at seconds. So 40 hours. Well, in order to go from hours to seconds, I know that I need to convert from hours to minutes to seconds. So I need those steps in my process. Well, I know that in 1 hour, there are 60 minutes. So I'm going to configure my fraction so that hours is on the bottom so that I can cancel them out. So I have 60 minutes per 1 hour. And I'm going to cross out my hours. So at this point, I'm now working with minutes. So I know that to convert from minutes to seconds, I know there are 60 seconds in 1 minute, and I want the minutes in the denominator so that they cancel out and I'm left with seconds. So I have 60 seconds in 1 minute, and haha, my minutes cancel. I'm left with seconds. So now what I have, running out of room, is 40 times 60 times 60, which is, what is that number? 28,800 seconds. So again, all this is just stepwise crossing out units. And I actually do recommend that you go through and physically cross out units, because at least for me, this is a way for me to make sure that I have it flipped the correct way. Side note, if, let's say, on a quiz, test, whatever type of assessment, y'all gave me this as the answer instead of scientific notation, this is totally valid. Totally good by me. I saw your work process. We're good. If you wrote it in scientific notation, so 1, 2, 3 times 10 to the 3 seconds. Y'all, this is also valid. Y'all, the sig figs here, that's not the important part. For me, it's that you use the correct conversion factors. So these are both totally fine answers. Example number 2. Let's say I have 50 grams of copper wire and I want to do some demos with it. And each demo takes 1.84 grams of wire. How many times can I do this demo? First, I'm going to write down, what am I given? So 50 grams of wire. And I know that the ratio I'm looking for is how much wire does each demo take? So in this case, for this word problem, our conversion factor is not as, I think it's harder to kind of see what it is in words here. So this is just something we're going to have to practice to get used to. I know that one demo takes 1.84 grams of wire. I can use this as my conversion factor. So I have 50 grams of wire times my conversion factor. So I want grams of wire. There we go. I want wire in the denominator. So 1.84 grams of wire per one demo. When I plug that into my calculator, so 50 divided by 1.84, I get approximately 27.2 demos. Y'all think about this answer for a second. Does it make sense if I could do 0.2 of a demo? No, this is an all or none situation. I can either do the demo or not. So I'm going to have to round down here and say that I can only do 27 demos. Our last and final example. So this example includes multiple conversion factors and also interpreting a problem. So words on a page into conversion factors. So one serving of ice cream is 0.5 cups and has 285 calories. I eat 3 cups. How many calories is this? Side note, y'all, this problem is not at all meant to be like counting calories, like shaming anyone for eating ice cream, okay? I love ice cream. It's delicious. Highly encourage if you're not lactose intolerant. I am working through this problem because calories are actually a very important unit in terms of chemistry. We're going to look at later on how calories are involved with energy and energy transfer and how reactions can happen. So that's why I'm introducing the term calorie here, okay? Not to say like counting calories or ice cream's bad. Ice cream is good. So let's go through. First off, I want you to recognize that this problem has a lot of good hidden information in it. If you remember from your math classes, there are certain words in problem-solving problems that mean mathematical functions. So one serving of ice cream is. The word is like saying equals. So one serving equals 0.5 cups. One serving is 0.5 cups and has 285 calories. This is also like saying equals. So what we're going to do is stepwise write down these conversion factors and figure out how to go from what I know to what I want. So cups to calories. Let's write these conversion factors first. I want to make a side note that as y'all become more comfortable with dimensional analysis, and as we go on through the school year, you might see those fractions, those conversion factors, written slightly differently, in a little bit of a different way, but it means the exact same thing. So, what am I talking about? Let's say I start with 12 inches, and I want to know how many meters this is. So I can say, I know that 12 inches times 1 foot has 12 inches. So that's conversion factor there. And the conversion factor for feet to meters, I'm just going to look this up, y'all. So there are 0.3 meters in 1 foot. Y'all, this is a weird conversion factor. I wouldn't super give it to this weird example. I'm just trying to show you the formatting. So we can solve it like this. We say 12 divided by 12 is 1 times 0.3 is 0.3 meters. So right now, the format we're using for this is to write out all of these fractions with parentheses, right? You might see this written like this. So we start with 12 inches, and then I know that 1 foot has 12 inches, and there is 0.3 meters, and 1 foot. Y'all might see this up here written in kind of this boxy format. This is literally meaning the exact same thing as up here. So everything up top is in a numerator, everything down below is in a denominator. You are more than welcome to use this format if you like it. I actually prefer it. Once you get more familiar with it, I think it's easier to work with, because to me it's visually easier to see what's going on. It's visually easier to say, this cancels with this. But again, both are totally valid, equal methods. So to wrap up this unit on scientific measurements, I want to talk about why dimensional analysis is important in chemical applications. It's nice that we know how to convert from, inches to feet and from meters to centimeters and all of that. What does this have to do with chemistry? For that, I want to talk about a specific chemical process. So humans commercially develop a lot of fertilizer, which is nitrogen-based, through the Haber-Bosch process. So the Haber-Bosch process is, y'all, it's so important to humanity in general. It created, this process creates so much fertilizer each year, and it has actually been attributed to helping boom humanity's population because we had more crops. So I want to look at this industrial fixation step. So again, we're creating this nitrogen-based fertilizer in factories. This is the fundamental chemical equation that is the Haber-Bosch process. So Haber-Bosch is the two dudes who developed it. So we're going to learn how to read these equations later on, but I want to start to prime your brain. What we're looking at here is 2 molecular hydrogens and 3 molecular nitrogens coming together to make 2 ammonia products. And we're going to talk about it later, but ammonia, so we see that N, this is that nitrogen fertilizer. What I want y'all to notice is that this reaction involves a specific ratio of hydrogen and nitrogens to make this many ammonias. So, we're thinking of ratios, we're thinking of conversion factors and dimensional analysis. Let's say we're working at that factory. Let's say we're developing this process. And we say, we have this much starting material. How much product can we make? How much fertilizer can we make? Y'all, this is a dimensional analysis problem. But instead of thinking it more in terms of like units like meters and, that type of unit, we're thinking about it in terms of chemicals. So that's why dimensional analysis is important. Actually, side note, if any of y'all go on to be, chemistry researchers, this process is so important because it helped us make way more food so more people could live. But y'all, it's actually like a huge consumer of water in the factories. And also there's the issue of runoff waste. So, we're learning about dimensional analysis now, kind of this fundamentals. But y'all, later on, like your generation and stuff is going to be solving a lot of these big problems. And it starts with understanding the basics. All right, let's look at one more example of why do we care about dimensional analysis. Okay, so what you see in this box is the chemical equation for cellular respiration. So yes, biology can be described with chemistry. So this is when we take in oxygen. So we see the 6O2 oxygen, and we see the C6H12O6. This is sugar, glucose. So we take in food and oxygen, and we breathe out, right? Carbon dioxide and water vapor, but we get energy out of it. So again, these numbers are specific. It has to be in this certain ratio for this process to create, the energy, the water, the carbon dioxide. So we're thinking of our biological system, and maybe we think about it more biologically, right? But ultimately, it's still chemistry. It's biochemistry, right? So those ratios, that dimensional analysis really comes into play. Alrighty. So this is the end of scientific measurements.